Say yes in the chat if you can see the screen. If you cannot, say no. Today is the first lesson of our third unit. We finished our second unit last time. So that was about linear modeling. So let's go over the homework from that. So this is our schedule for today. Unit 3 will be over functions. So I know some of you that have taken my last class called Basic Algebra have learned about functions and their transformations. But this unit, we are going to go more in depth about it. And then we're also going to learn about function inverses, which is very important. So let's just start with the first problem from the homework. So I'll give you like a few moments to put your answers for the homework in the chat, and then I'll go over it. This shouldn't be too hard. It's just a standard equation. All right, let's go over this one. So this one is should be a little bit of review because most of you should be able to know what a standard form equation is. So first, of course, we are given 2 points. So we need to pay attention to that and find the slope from those 2 points. And then we're going to put that into point slope form. So remember when I told you that you only need 2 points to make a point slope form equation, and then you can convert it to a standard form. So let's just do that with this 2 points. So the slope is going to be equal to 1 plus 3 over 9 minus 2 equal to 4 over 7. Right. because it will just be the y minus the difference in y over the difference in x. And then we can go to the point slope form now. So recall it is y minus y1 is equal to m times x minus x1. So we already have the m, the slope, and we just need to pick one point. So let's pick like 9, 1. So y minus 1 is equal to 4 over 7 times x minus 9. From here we get y minus 1 is equal to 4 over 7x minus 36 over 7. So this is quite a disgusting one, but that's fine. Actually, we can simplify it a little bit more later on. So y is equal to, actually, let's move the x over here. Y minus 4 over 7x is equal to negative 36 over 7 plus 1. And 1 is 7 over 7, so this is going to be y minus 4 over, actually, we can multiply everything by 7 because you can see that these denominators are the same. So let's multiply everything by 7 first. So then we are going to get 7y minus 4x is equal to negative 36 plus 7. And that's it. Negative 4x plus 7y is equal to negative 29. That is the standard form. So I understand if you got something like with fractions, but always try to see if you can simplify it. So William, your answer is totally fine, but make sure if you can simplify it like this. Okay, so let's move on to the second question. A charter fishing company buys a new boat for $154,900 and assumes that it will have a trade-in value of $46,100 after 16 years. So you have to do A, B, and C. First, of course, you have to create a model, an equation for the depreciated value of this boat. So as time goes on, this boat is going to be, it might break or something, and its condition is going to get worse. So of course the value is going to go down. So we need to find an equation for that. And then you need to interpret the slope. And then finally, in which year will the depreciated value of the boat fall below $100,000? So I'm going to give you about 4 or 5 minutes to put your answers in the chat. And if you haven't already, try this. So this is the main thing that I wanted to do last class. So make sure you understand how to model these situations with linear models. All right. So let's try to do this one. Actually, I'm gonna give you guys a little bit more time because not many people have given me answers yet. So I'm gonna give you 1 or 2 more minutes to do this. So make sure my hint to you is to find the slope first, obviously, because you're given 2 points, right? Here's the 2 points: 0, 154,000, and then 16, 46,000. These are the 2 points you're given because X is the number of years after the purchase. So then you can find the slope from these 2 points and then finally make an equation. All right, let's go over this one. So first, of course, we need to find the slope. So that's just you're going to subtract the y values. Let me pull up a calculator. It's going to be 108,800 over negative 16. So since, of course, the value is decreasing, that means the slope is going to be negative. So when you divide that by negative 16, going to be negative 6,800. That's going to be the slope. And putting it into point slope form, we can just pick a point. Let's pick this one. You're just going to get y minus 154,000 is equal to, well, 900 is going to be equal to negative 6,800 times x minus 0, which is just x. And then to find your equation, you just add. Right, so that is your equation. And when you interpret the slope, so this is the equation. And how do we interpret the slope? We can interpret the slope because it's negative 6,800. So basically it's over 1, right? So for every year that passes, the value decreases by negative 6,800. Oh, well, decreases just $6,800. And finally, the C is going to be, in which year will the depreciated value of the boat fall below 100,000? So first, let's find when it's below 100,000. That's y is going to be equal to 100,000, equal to negative 6,800 x plus whatever this is, and we can just solve. So x should be equal to, if you just subtract from both sides, it's going to be around 8.07. But so basically we can say after 8 years, because since it's only 8.07, that's pretty early in the year, right? So maybe later in the year, this boat will fall below $100,000. Okay. And second of all, a drugstore sells a drug costing $85 for $112, and a drug costing $175 for $238. So I'm just going to go over this one because we need to hurry up. So this markup is quite common in drugstores and other retail stores. You can see when you go to buy something, the brand prices are usually pretty expensive because they need to earn money. So there's usually this markup policy can be denoted as linear. So we can find an equation for this. So you're given 85 and 112 and 175 for 238. So when you decide the points, you need to know that 175 is the original price. It's the wholesale price that they buy from the brands and then resell them. 238 is the markup. So that means 175 is an independent variable, meaning it's the x. So then from this, we can find the slope is 238 minus 112 over 175 minus 85, which is going to be equal to 238 minus 112 is 126 divided by 175 minus 85 is just 90. So this is a weird one. 1.4. Okay, so that's our slope, and we can put that into a point slope equation. Let's just pick this point over here. Okay, and we have y is equal to 1.4x, and let's see here, 1.4 times negative 85 is negative 119. Then you add 112, which is just equal to negative 7. So that's our equation here. Put that here. And we interpret our slope, which means we can interpret this as the ratio of the markup to the original. Well, yes, for every dollar increased of this, well, not necessarily the ratio. That's wrong. For every dollar of the original, the markup increases by $1.4, like that. Okay, so number C is going to be equal to, well, what does a store pay for a drug that retails for $1.85? So that's just going to be equal to, just put that in the equation. Of course, you get this, move this to the other side, you get what? 192 is equal to 1.4x. X is equal to about, hold up. Did I do this correctly? So 170, yeah. Let me see here. 185 is equal to 1.4. Does anybody see a problem here? Because when I solve this equation, it's 185 plus 7 divided by 1.4, which is 100. No, I did it wrong, right? 192 divided by 1.4 is equal to 137, which shouldn't. Oh, never mind. We're talking not about the original. I see. Okay. Yeah, so that is correct. It is $137.14. Okay, so that's basically the linear modeling. You need to learn how to interpret the slope in real life situations, and then also use the equation that you derived to solve similar problems like this. Okay, so now let's move on to basic graphing concepts. So I'm sure you guys already know what a function is, so I don't really need to explain that much about that stuff. Remember, a function, no x can correspond to two y's, because then it's going to violate the vertical line test, which means it's not a function. So one x cannot correspond to more than one y. However, it is possible that multiple x's correspond to one y, like so. Like for example, if you have something like this is totally possible. Multiple x's corresponding to one y, like this. This is possible. This is still a function. So just make sure it has to pass the vertical line test. So basic graphing concepts, let's see here. So remember to notice the domain and range. The domain is always going to be the set of all x's that satisfy this. The range is the set of all the y values, and we maybe come across new word here, continuous, continuity, continuous, meaning that there are no gaps or breaks. So if you have something like this is continuous because there are no gaps and breaks, meaning that you can draw the graph without picking up your pencil. However, something that is not continuous is something like this, where it breaks off. That is not continuous because you have to pick up your pencil. So it's pretty straightforward, right? And finally, I want to, well, there are two more things. One is a constant function. So a constant function is going to be looking like this. It's when it's basically horizontal, meaning it's not increasing or decreasing. So what is increasing or decreasing? Increasing means that the graph rises from left to right, like this. Decreasing means that it dips down, it falls left to right, like this. And it kind of directly corresponds to the slope, because this is a positive slope, this is a negative slope. And when there is no increasing or decreasing at all, it is just constant, a horizontal line like this. So those are the basic graphing concepts that you need to know. So let's go over finding domain again, because we might need to use it later on. So when you find the domain of a function, let me just give you an example. 2x squared minus 8 over 9 minus x squared. So I'm pretty sure some of you have done this. So William, yes, William. Would you like to volunteer to help me solve this? How would you find the domain?
So to find the domain, you have to see what values x cannot be, and x cannot be 7. So the domain is that x cannot be 7.
Yes. So when you're finding domain, exactly, you have to look for restrictions. The only restriction on this thing is the denominator. Whenever you see something divided by something else, always look at the denominator, because the denominator can never be 0, because you all know that something divided by 0 is going to be undefined. So that means the restriction 49 minus x squared cannot be equal to 0. William was a little bit right, so we need to factor this. And you see there are two factors x cannot be, not just 7, but also -7. X cannot be equal to either of those numbers, meaning that the domain has to be equal to -infinity to infinity, excluding these, skipping over them.
Oh wait, I also have another question.
Yes.
So what is the wait, can I annotate please?
Are you able to annotate?
No.
Oh, what do you want?
Like I wanna show a graph where multiple y values could correspond to 1x.
Multiple y values correspond to 1x.
Yeah,
So like this.
yeah.
What about it?
Is that possible to graph on?
Yeah, you can graph these, but they're just not a function. A circle, you can graph a circle, and that's not a function.
Oh.
You can graph a lot of things that are not functions. For example, you can graph something like something that you don't traditionally use function notation to graph. Something like, I don't know, like this. You can graph this. I've done this before. It's like a polar graph with polar coordinates, but you don't use regular function notation to do it. Just like a circle is not a function. This notation will only graph functions, but of course, you can graph a lot of other things that aren't functions. But we're not going to go that deep because all we're doing is learning about functions. It's a lot of times it's difficult to graph things like that. Does that answer your question?
Yeah, thanks.
Okay. Now we're going to learn about piecewise functions. So we're going to get into some pretty weird functions here, but piecewise functions are very, very useful. You'll learn them in pre-calculus, calculus, you'll still use them. Okay, so piecewise functions are basically just splitting the function into different parts. It's very useful. So let me just give you an example. Piecewise, for example, is going to be equal to x plus 1 if x is less than 0, and negative x, 2x plus 3 if x is greater than or equal to 0. So all this does is it basically splits our graph. And we can graph multiple different functions in one function. It's very useful. So it says, and it goes by these domain restrictions. So in this domain where x is less than 0, the function is going to be x plus 1. So it's going to be something like this. It's going to be the function. But after we cross the 0, when x is greater than or equal to 0, it's going to be negative 2x plus 3. So it's like something like this. And notice that I used an open circle and closed circle here, because the domain of this is strictly less than 0, meaning it can't actually touch 0, while this one can equal to 0. So make sure you are careful about that, but don't worry, there won't be any homework questions about this. I just wanted to introduce piecewise functions today to we're not really working that much with piecewise functions because algebra 2 doesn't really do much with piecewise functions, but you'll definitely learn more about piecewise functions when you get into calculus, because you use piecewise functions a lot in calculus. And then let's talk about step functions. So step functions literally looks like stairs. Like they're the closest you can get to stairs, I think. So it's also called the greatest integer function. GIF. Very convenient. Okay. And it also looks pretty weird too. It's f of x is equal to a bracket, double bracket x. Looks like that. That's what it looks like. It's double bracket. That's how you can tell if it's a greatest integer function. So what's the definition of a greatest integer function? That means f of x is the greatest integer less than or equal to x. So what does this actually mean? Let me give you some examples. So what is the greatest integer function of 3.1? The definition expressly tells you that the greatest integer less than or equal to x. So what is the greatest integer less than or equal to x? That would be 3. You have to go down on this one. Sometimes you round up, but not for this. You always go down. And we can exploit that in our graph later. What about negative 3.1? So make sure you pay close attention to this. It's actually -4 because -4 is less than a -3.1. And another example is 3. Just 3, it says the definition tells you the greatest integer less than or equal to x. So in this case, it is just 3. So now I think we can start to visualize what our graph is going to be look like. So from these couple examples alone, you can kind of see what the greatest integer function is like. So when x is 0, when x is 0 or 0.5, the greatest integer function y is still going to be 0. It can be 0.99999. It's still going to be 0 because it's the greatest integer less than or equal to that 0.99999. Right? So you're going to let me do this in a different color. I think it'd be better to see. So blue. So it's like this. So as you go along, as long as you stay less than 1, the greatest integer function is going to be 0. But when you get to 1, that's a different story. There's an open circle there because it's not going to be equal to 1, 0 anymore. It's going to be equal to 1. And the same for 1. The greatest integer function of 1 will be equal to 1. The greatest integer of 1.9 is still going to be 1. And so on. 1.99 is still going to be 1. But the moment you cross the 2 threshold, it's going to jump up. So instead, we're going to have a graph like this. It really does look a lot like stairs. And the same for the other side. The same for the other side, like this. It's going to be looking like this. It's quite weird. So that's what a step function is. So we aren't really going to use the step functions or the piecewise functions just yet in this lesson, but we will later on when we get into more advanced topics. So the greatest integer function, how to graph it, just trains you to be able to graph these functions by just thinking about the nature from the definition of the greatest integer function without even equation. We are able to get a graph from it. It just tells you shows you how to critically think about what you're graphing, and make sure you pay close attention to the definitions of functions. So now let's go on to what we are really here today: rigid transformations. So I know some students have already been through the basic algebra course that I've been teaching in the past, and they have learned about the rigid transformations, but it has been quite a while. So some of you might have forgot. And this class, we are not just going to be going very shallow. We're going to go quite deep into the subject and make sure you thoroughly understand why this happens. So let's again remind ourselves of the 4 parent graphs. Now, these aren't the only parent graphs. There are so many more parent graphs, but these are the ones that we're going to focus on in Algebra 2 because they suit our purposes. Some we've already learned, like f of x is equal to x. We're not going to bother with that. We already know that. So let's move on to some graphs that we are not yet too familiar with. So the 4 parent graphs we're going to be exposed to today is going to be x squared, x cubed, absolute value of x, and finally square root of x. And I think most of you should know what this looks like, right? X squared, like a u, x cubed, like this snake thing, absolute value of x, like a v, and finally square root of x is just this weird thing here. But if you don't know, you can go on desmos.com and you can put that in. But you can always do like a table of values, like what is 1 cubed, 2 cubed, negative 1 cubed, negative 2 cubed, and you can graph it yourselves with the table of values. Okay, so now let's go on to what are our rigid transformations. So what are rigid transformations? We know that we can transform functions, right? We've all heard of that. We can change, like translate, reflection, translation, transformation. We've all heard those terms, right? Um, like fifth grade or something. Translating everything, reflecting the graphs, the shapes, the pentagons. Okay, so rigid transformations are rigid because they only change the location, not the shape. So, meaning that a rigid transformation of, let's say, a parabola would be equal to like changing like where it is, whether it's here, here, here. That's a rigid transformation. A non-rigid transformation would be like changing its shape, like this, making it wider, making it thinner. That is a non-rigid transformation that we are going to cover next class. So this class, we're going to cover the rigid transformations, which are horizontal shifts, vertical shifts, and reflections. As you can notice, these don't affect the shape. The graph will still look same, like shape-wise, but the location is just going to be different. So let's look at the types of transformations. Horizontal transformation. This is f of c minus a. Well, f of x minus c. F of x minus c. This is f, right? This is f, maybe. F of x minus c is going to be this, depending on what c is. So here are a couple of guidelines. Because the change is directly in these parentheses, that means it is directly a domain change, meaning that f of x minus 2 is it's not going to be moving left by 2, it's going to be moving right by 2. If you look at the domain, let's say this is 0 and 4, the domain is 0 and 4. So if you put the change x minus 2, the change inside the domain, the current domain, you can see that the change in domain is going to be shifting right, meaning that it's going to be, when you solve for x, it's going to be equal to in between 2 and 6. So when you horizontally transform this, make sure that when you're subtracting something, you're actually moving it to the right, and when you're adding something, you're actually moving it to the left. Next is vertical. Vertical, very simple. It's f of x plus c. As you can see, y is equal to f of x, right? Y is equal to f of x. So this c is not affecting the x's anyway. The domain is not changing, except the y value is changing the range, because the c is adding to the y, right? The range is getting added on to by the c. So this is probably, let's say this is f of x, and you have f of x plus 2. All you're doing is moving this up by 2 units. Very simple, like this. Moving it up by 2 units. Finally, reflections. There are 2 types of reflections. One's domain change, one is not. So there are 2 reflections, of course, across the y-axis and across the x-axis. Across the y-axis, meaning that it's left to right. Across the x-axis, meaning it's up and down. Now, left and right, that deals with the domain. So this reflecting over the y-axis is going to be a domain change, f of negative x. Reflection up and down across the x-axis is going to be a range change, meaning it is going to be negative f of x. It's on the outside. All range changes are on the outside, while the domain changes are inside of the parentheses. So those are the reflections. Are there any questions? about this. You'll see when I show you some examples. So without further ado, let's go and look at some examples. But before that, let's just knock this out, right? Find the domain of f of x is equal to 4x minus 1 and x plus 6. So remember, you have to look at the restriction. When you look at the restrictions, let me tell you, there are two most common restrictions that you'll ever see in Algebra 2 and beyond. These two very common restrictions are denominators and roots. What do I mean by that? This one is a denominator. So what's a restriction on a denominator? It's just that it cannot be equal to 0, right? It cannot be equal to 0. What about roots? Talking about square roots. Like, for example, square root of x minus 3. X minus 3 must be equal to a greater than or equal to 0. Otherwise, taking the square root of a negative number, you can't do that, right? So that is the restriction. Therefore, the restriction is that x has to be greater than or equal to 3. So now let's do this problem. What is the domain restriction? Well, obviously, it's the denominator, right? So 4x minus 1 times x plus 6 cannot be equal to 0. So therefore, x has to be cannot be equal to 1/4, and it cannot be equal to -6. Taking these in mind, we can look at our domain here. It's going to be like this. So these are all the intervals. And of course, there's a union sign. Yeah, a union sign connecting all of those intervals. So remember, you have to skip past these. Now let's look at our last one, which I really want to touch on. This time, g of x is an actual function, square root of x. So we need to write an equation if it's shifted by 3 units reflected over x-axis and shifted down by 2 units. So write the equation if it's shifted left by 3 units. That's a domain change. It's shifted left. Next, it's reflected over the x-axis, meaning it's reflected up and down. That's a range change. Shifted down, that's another range change. So first, let's deal with the domain change, which takes priority because it changes the domain, which is the most important thing here. So our original thing is going to be x, right? It's shifted left by 3 units. Remember what I said. If you're subtracting something, if you're subtracting c, it's going to be shifting right, meaning that when you add a positive c, it's going to be shifting left, meaning we have to add 3 here inside the parentheses, which in this case is the square root. You have to shift it left by 3 units, and then we have to reflect it over the x-axis. So how do we do that? Again, we have to add a negative sign outside the parentheses here. So then g prime of x, the new equation, is going to be equal to negative the square root of x plus 3, and then finally shifted down by 2 units is -2. So that wasn't too hard, right? So the homework will be similar to this, as we have not learned non-rigid transformations yet. So the rigid transformations we covered today, and we'll cover the non-rigid transformations next class. So I think that is all for today. So thank you everybody for coming today. Now see you next week. So are there any questions?
Do you
If
know
there are
when
no
the homework's
questions,
going to be out?
yes,
Do you know when the homework's going to be posted?
homework probably tonight. And I haven't gotten around to grading the last ones yet, so I'll grade that soon. Okay, I'll see you all next week.
Bye. Thank you.
Thank you.